Something that we're going to be using in a lot of our calculations for relativity is something called the Lorentz factor. We use the Greek letter gamma for this, and I draw gamma like this. Some people think when it's written in a font form that it looks like a Y, but it's not quite like that. It's one of those examples where the typed and written form look a little bit different. So I do it look like this, a fish that is swimming downwards. So the quantity gamma is used to determine changes in lengths and times, but not actually masses. I realise that's an error that I left in from my previous notes. There's been a change in the physics understanding, so we're not going to talk about changes in masses here, so please omit that from your notes. So gamma is calculated using this. It is a bit of a fun equation. We've got a fraction and we've got a surd on the bottom and then a fraction within the surd. But basically we're going to be looking at a very important ratio here. So we're going to be talking about v being the velocity an object is traveling. We frequently will be looking at like spacecrafts, or I don't know, that's the main thing we seem to look at, spacecraft. And c is the speed of light. Now the really cool thing about the ratio as it's written is we've been dealing with a lot of velocities as a fraction of the speed of light. So, for example, we talked about things last lesson where we said something was going at 0.8 c. If we just look at this portion here, v squared over c squared, so let's do v squared over c squared, that ratio is going to give us whatever 0.8 squared is, times c squared over c squared. So if you leave things in terms of c, you don't actually need to substitute in 3 by 10 to the 8, or the square of that, 9 by 10 to the 16. You can just cancel off the c squareds here, so you just be left with 0.8 squared. When you put that into the formula, you'll notice, try a few different values of fractions of c. Try 0.1 c, 0.999 c. The fact is, gamma's always got to be greater than 1, and I want you to convince yourself of that mathematically by trying some different values of c. We can't have a velocity of an object larger than the speed of light, so we won't be able to put in values like 1.1 c. So gamma will always be larger than 1 because this fractional amount on the bottom is always going to give you a value smaller than 1, and 1 divided by something smaller than 1 gives you something bigger than 1. That's a mathematical explanation, what I just spoke about there. That's not an explanation we'd give on an exam. Physics explanation is the value of v has always got to be smaller than the speed of light because objects with mass cannot travel at the speed of light. That therefore gives a Lorentz factor or a gamma value of larger than 1. Oh, whoopsie. So a really handy graph to be aware of, because I've seen questions that directly reference this graph, is this one here. The gamma value based on the percentage of the speed of light. You're going to see how we're going to use this gamma value later, and the fact that it's equal to 1, we're relatively low values of the speed of light. That's why we don't see those weird relativistic effects we're going to explore in everyday life. Because the gamma value, what's going to be shifting length and time, is just 1. So we're multiplying things by 1, we're not noticing a difference here. But when we start approaching the speed of light, we actually get a limit. Because it's a limit, we actually have an asymptote at this 100% point. If I used a ruler and a pencil, that would be better. But there's an asymptote here. It cannot reach that 100% here, and the gamma value would actually continue off to infinity. Another important feature of this graph, we said gamma was always larger than 1, so 1 is at this axis here. It doesn't go to 0, it doesn't go through the origin here. It starts at 1 and then increases in value, and it's a significant increase in this region towards the 100% here. So let's do some examples actually calculating this. We're told in a particle accelerator, some magnesium ions are accelerated to 20% of the speed of light. So I could write that as 0.2, I need 0, 0 to have sig figs, c. Which one of the following is the closest to the Lorentz factor, gamma, for the magnesium ions at this speed? So let's actually practice using that equation. So it's 1 over square root of 1 minus v squared over c squared. So I find it convenient. You don't need to do it like this to do the v squared over c squared separately and then substitute it back into gamma. I don't know. You completely don't need to do that at all. I'm just really aware of the double-decker fraction action we've got here. We said the value of v was 0.200c. Don't need to really worry about putting 0.200c in here because we're doing a multiple choice question, so I'm going to be lazy and just do 0.2c. We need to put that all in brackets and square it. You're not just squaring the c value, you need to square the 0.2 portion over c squared. 0.2 squared is going to be 0.04 c squared, because we've got to do the c squared in this as well, over c squared. And as I mentioned before, we can cancel off those c squareds. So that means our Lorentz factor is going to be 1 minus, we've got 0.04. That was the value of v squared over c squared that we did over here. Alrighty, our value of gamma is 1.02. Brilliant. So that's how we do this. As I said, I like to do v squared over c squared separately. It just seems to make things a little bit neater. You don't need to do that. You could have done all of this working out combined. We're now told about an electron that has 100 mega electron volts of energy. We're going to be looking at these energy units a little later on. I'm pretty sure this is a question from a previous exam where future questions relied on this data as well. What we care about is that the electrons are traveling at 99.9% of the speed of light, and we're asked to find the Lorentz factor for the electron. So 99.9% of the speed of light, that could be written as 0.999c. So I'd like you to go ahead and figure out what the Lorentz factor is here. As I said, you might like to do it all in one and put the v squared over c squared directly into this formula, or you might like to do v squared over c squared separately just to be able to determine that. So with this question here, we get 22.4. I'd really like you to experiment. What if you had, instead of 0.999c, what if you had 0.9999c? What if you added another 9 onto the end to that? Oh, it feels like this is a question that we were training for. It says, which of the following diagrams best represents the gamma Lorentz factor versus speed for an electron that is accelerated from rest to near the speed of light, c? So we know definitely B is wrong. That's a straight line. We know we're anticipating a curvy line. We can't have a gamma factor of less than 0 or equal to 0. So we're left with D. It's got to start with a gamma value of 1 on this axis here. And we know it's got to have that curve and that asymptote.